So let's take a little bit and let's review the functionality of the urinary system. Okay? And as always, make sure you know the structures as they're listed in lab and the functions that go along with them. But what we're going to do right here is focus on the actual function of the urinary system. And in reality, at the end of the day, the function of the urinary system is to filter the blood and create a substance called urine that contains all the waste molecules and excrete that from the body. So let's just look at our nephron. And before we get started, let's review the parts of the nephron, and I'll attempt to draw them out. We know we start with a capillary bed. The capillary bed is the glomerulus. Wrapped around that capillary bed is a three-dimensional kind of cup-shaped structure. That is the Bowman's capsule. And the Bowman's capsule is actually the beginning of the nephron. Attached to that are parts of the renal tubule. So the first part is the proximal convoluted tubule. And then that straightens out and goes down and up the loop of Henle. And you know we have a descending limb and an ascending limb that behave differently. After that, we go to another twisted up tube. That's distal convoluted tubule. And then sometimes the story gets interesting. Essentially, distal convoluted tubules dump into collecting tubules. Every now and then, a book will call that a collecting duct. I learned that that's the duct and that's the tubule. So what do? Well, we're going to default to the lab manual. So just be flexible, and as I will be, hint, hint, in understanding that sometimes there's two different words used here. But the word collecting is always used, so that's good. So we know functionally that filtration takes place there at the renal corpuscle, and the function of all of this other stuff is reabsorption and secretion. So let's begin with filtration. And as we looked at in lecture, filtration is not specific. I'm not filtering one molecule versus another. I'm filtering fluid with small things dissolved into it. And that it's actually a function of pressure gradients. So if this is my afferent arteriole, this is my glomerulus in here, that's my efferent arteriole. One of the things to notice is the size difference between these two arterioles. Well, the afferent arteriole is much bigger than the efferent. So a lot of blood comes in, but a lot of blood can't leave at the same time. So you can kind of imagine that blood backs up a little bit in this glomerulus. Well, that creates a high pressure capillary bed. We're not really used to that. Capillaries, blood goes into the capillary bed, pressure drops, and it's pretty much zero back the other end. This one's not going to work that way. So the glomerulus is a high pressure capillary bed. It's also fenestrated, and it has cells wrapped around it called podocytes. Well, the moral of that is that this is a capillary under high pressure that has a lot of holes in its wall, and then the size of the holes is controlled by the cells wrapped around it. So if we measured the pressure of the blood inside the capillary bed, we'd find out it's pretty high. And that pressure is forcing or pushing or squeezing fluid and small molecules out of those filtration slits. So the pressure of the blood in the glomerulus itself, the glomerular blood pressure, also known as glomerular hydrostatic pressure, is a force pushing out of the glomerulus. And it can be changed moment to moment, day to day. It's a direct result of how much blood is in the glomerulus. If I put a lot of blood in there, like my afferent arterioles, nice and wide, lots of blood in the glomerulus, I'm going to have high pressure. If I squeeze my afferent arteriole so the diameter is much shorter, less blood goes in the glomerulus, and then I have low pressure. But whether it's high or low, it is a force pushing out. So it's going to, again, push small molecules, water, glucose, amino acids out filtration slits. And it can be changed very easily by changing the diameter of that arteriole. These other two forces are forces pushing back in. And these change, but not on a moment-to-moment basis, not very easily, and so we can kind of think of them as staying relatively constant. One of them is due to the fact that there's proteins inside the blood, and the proteins are too big, they're never coming out, but they draw water toward them. So imagine water molecules being drawn into or attracted into the glomerulus. That force is called the blood colloid osmotic pressure. The second pressure pushing in is this one right here. This is called capsular hydrostatic pressure, and it comes about because filtrate fluid backs up in this Bowman's capsule and pushes up against the glomerulus. So that's what that one is. So again, one force pushing out, two forces pushing back in. As long as I can keep the force pushing out greater than the forces pushing back in, then there's a net movement of fluid out. And remember, it's water and small molecules dissolved into it. And that's pretty much the mechanism behind filtration. So again, imagine a molecule of glucose or an amino acid. These are small. Water, ions, you can imagine some gases in there, and let's throw in some urea for good measure. These molecules are all relatively small, and so the fact that the pressure in here is greater than the pressures over here forces these molecules through filtration slits into the space here within the Bowman's capsule. At that point, we're going to call this liquid filtrate. I can spell. And filtrate is going to start to move through the next part, which would be the proximal convoluted tubule. The job of the rest of the nephron is to capture all the nutrient molecules and return them to the blood supply, and allow all these waste molecules to come out the other end of the urine, the other end in urine, I should say. So our ability to do filtration here is dependent on the fact that we have a pretty permeable membrane. Remember, it's fenestrated with slits caused by podocytes. We have this glomerular hydrostatic, or this blood pressure, pushing out, and then we have an osmotic pressure and we have a hydrostatic pressure. Right? We got two pressures pushing in. The difference between the out versus the in is called net filtration pressure. That's what's actually going to drive filtration. Now, since these two stay kind of constant, the only way I can easily change the net filtration pressure on a moment-to-moment basis is to change the blood pressure inside the glomerulus. Remember, that's kind of easy to do. All I have to do is either dilate or constrict my afferent arteriole. So if we were to mathematically represent net filtration pressure, here's what we find. The blood pressure inside the glomerulus, subtract off the osmotic and the hydrostatic pressures. So net filtration pressure is the pressure out minus the two pressures pushing back in. The greater the difference here, the larger the net filtration pressure is, the more filtration we get. So if we need to excrete a lot of water and get rid of a lot of urine, we're going to do things to make sure we have a high net filtration pressure, in which case we'll get a lot of filtration going on. If I forgot to drink water and I needed to conserve water in urine, then I'm going to have a low blood pressure, so a low net filtration pressure. In lecture, I said they're all positively correlated. So if I had an increase in blood volume, an increase in the amount of blood in the capillary, I'm going to increase glomerular hydrostatic blood pressure. If I increase that, I'll have an increase in net filtration pressure, which causes an increase in the speed in which I filter, or the glomerular filtration rate. So the one nice thing about all these terms is they're positively correlated. If you raise blood volume, you raise everything else. If you drop blood volume, you drop everything else. So here's that term I said, glomerular filtration rate. It's basically the speed at which we filter, And what determines that is the difference between the pressures, and what determines that is really the blood pressure in the glomerulus. And so you don't want to filter too much. If the filtration rate is too high, you're going to be making lots of filtrate and lots of urine. But the problem with that is that you don't give the cuboidal cells in the tubule enough time to reabsorb. So we're going to lose a lot of nutrients in the urine, and we don't want that. We also don't want it to be too low, because if filtration rate is low and only small amounts of filtrate are moving through, we give the cells, the cuboidal cells, too much opportunity, and they reabsorb everything, even waste molecules. So we want to find some happy medium between the two. We want that solution to this problem to be flexible, so that no matter what's happening in my body, I can either increase or decrease rates to meet my needs. So in order for us to regulate the filtration rate, we're going to rely on multiple mechanisms. One set of mechanisms is intrinsic. It's inside the organ. Okay? And it's self-regulation. And we have two options here. So we're going to look at the myogenic mechanism and something called the flow-dependent tubuloglomerular mechanism. So two methods inside the actual organ itself that can allow us to change filtration rates. We can also utilize our sympathetic nervous system. So we're going to kick this one into gear if we're scared. So we'll look at the effect that the sympathetic nervous system has on filtration rate. And then we're also going to look at two hormonal pathways here that are extrinsic as well and help us regulate filtration rate. So before we look at them, remember what filtration rate is. Glomerular filtration rate is basically the speed at which you make filtrate. If it's high, you're making lots of filtrate and you'll have watery urine. If it's low, you make less filtrate and you have a more concentrated urine. What determines GFR, glomerular filtration rate, was the net filtration pressure, the difference between the out versus the in. And what determines that is glomerular hydrostatic pressure, the pressure of the blood in the glomerulus. And lastly, I control that by volume, how much blood I actually put in the glomerulus. Alright, so intrinsic autoregulation, myogenic, that prefix right there, myo, means muscle. So that deals with the smooth muscle in the blood vessels and the fact that they can respond to stretch. This other one, this flow-dependent one, is dealing with the juxtaglomerular apparatus, a collection of different cell types that's nestled between the arterioles and the glomerulus itself, and the Bowman's capsule. Myogenic autoregulation is kind of simple, and again, it's innate property of smooth muscle. If you add blood to the arteriole, you stretch its walls, and the smooth muscle responds by constricting. So this, on a moment-to-moment basis, is one way of trying to keep the amount of blood in the glomerulus kind of constant, so that you don't have rapid falls and rises in the amount of blood. So we're trying to regulate and intrinsically keep flow relatively constant. That's never going to stay totally constant, but this is one layer and one attempt at trying to do that. And that's it. Tubuloglomerular feedback utilizes macula densa cells that we find here. Notice how they're on the ascending loop of Henle. And then we have another collection of cells that I call JG cells sitting over there. Notice how they're near the afferent arteriole. So that whole thing together, that's the JGA. So let's go see what these cells do. All right, macula densa cells we saw are on the ascending loop of Henle. You know, that's the part of loop of Henle that pumps salts. So what these cells do is they monitor the salt concentration in the filtrate. If the salt concentration in the filtrate is low, that tells these cells that the filtration rate is much too slow. So those cells up in the proximal convoluted tubule have way too much time on their hands. They're reabsorbing way too much solute. So again, a low sodium chloride or low salt concentration in the filtrate is a signal to macula densa cells. It stimulates them. And they read that as the GFR being too slow. So do we want to leave it slow, or do we want to raise it back up again? And obviously the answer is we want to get it back up again to homeostasis. So the way we're going to manipulate that, remember, if I increase the volume of blood in the glomerulus, I increase the glomerular blood pressure, which means I increase the net filtration pressure, which means I increase the rate. So if I have a low rate, all I have to do is get more blood into the glomerulus and everything else falls in place. So that's what we see here. The macula densa cells dilate the afferent arteriole so that more blood comes in, pressure rises, rate rises. The other thing they do is they stimulate the JG cells to secrete renin. You see that over here. And it turns out JG cells, not only can they be stimulated by macula densas to secrete renin, they're also stimulated by the hormones of stress to secrete renin. So let's take a look at renin. We'll come back to this one. Renin, once we secrete it, remember, causes the conversion of angiotensinogen to angiotensin II. And angiotensin II does two things. It's a potent vasoconstrictor, so it increases blood pressure throughout the body. It also causes aldosterone secretion. Aldosterone acts on the renal tubule and causes an increase in sodium reabsorption. And remember, where sodium goes, water follows. So that's a sneaky way of increasing blood pressure. So renin-angiotensin is a blast from our past. We looked at it before, the same pathway before, when we talked about blood pressure. All right, so now back here. Extrinsically, I can manipulate the amount of blood in that glomerulus and then everything after that with the sympathetic nervous system. When we're at rest and nice and calm, afferent arterioles are vasodilated, so plenty of blood goes in, everything is high. But under times of stress, you know, I said in class, if for your ancestor, if something scary was chasing it, you couldn't stop and pee and say, hey, wait a minute, bad guy who wants to kill me, give me a second, I gotta pee, I'll come back. So in actual times of stress, when you're in the moment, you inhibit urine formation. And what happens is you increase the number of sympathetic action potentials, and they cause vasoconstriction of these arterioles. That means less blood in the glomerulus, less volume, less pressure, less net pressure. You got the story. Less filtration. We can also accomplish the same task with the hormones of stress, epi and norepi, and that renin pathway falls into the category of a hormone as well. So you can see renin's kind of important, and renin is something that we get by a lot of mechanisms. Okay, the JG cells themselves, if they're not stretched, they'll secrete renin. We can stimulate them using a macula densa cell to secrete renin, and really renin acts by its friend and causing the production or conversion to angiotensin II. Alright, so other things we can do at the same time. Remember, I've said it a lot, but now, if something's really, really important, the body tends to be redundant. It tends to have more than one way to get the job done. So should you ever need to increase your rate, remember, in order to increase that filtration rate, I have to increase the actual volume of blood entering the glomerulus. And so we do that by dilating the afferent arteriole. So prostaglandins, and you can see angiotensin II falling in that category. This is sympathetic nervous system stimulation. Prostaglandins are a whole other set of hormones that we don't get to talk about, and there's tons of different prostaglandins. But there's a set of prostaglandins that are vasodilators. Also, the endothelium of a blood vessel itself can secrete nitric oxide, which causes it to dilate. On the other extreme, here's two constrictors, adenosine from blood vessels, and endothelin, which actually comes from cells of the renal tubule. So again, more than one way to get the job done because filtration rate is important. Well, once we're all done doing filtration and we got our rate at a point where it meets our needs, that filtrate member goes down the rest of the nephron. And so the job now is to look at that filtrate and recycle, bring back all the nutrient molecules. That's reabsorption. And just keep in mind that when we bring back these nutrient molecules, we're going to have to bring them across a couple of membranes, a couple of layers of cells. So we have a little bit of work to do here. So throughout the different parts of the nephron, here are different things that are reabsorbed. And you can see by far the proximal convoluted tubule is reabsorbing, tons of nutrients. The loop of Henle reabsorbs water because it pumps salts. The distal convoluted tubule, for our purposes, is more involved in reabsorbing ions and some water. And then the collecting duct can do urea for osmosis, water-salt balance. But what we're going to focus on is water, the ability to reabsorb water one more time. The other thing I pointed out in lecture is how you see sodium show up a lot, and we'll get to that. So keep in mind whether we're trying to reabsorb nutrients, water, or ions. Some of it is by passive transport, and some of it's going to be active transport. Either way, molecules can be transported across the actual cell to the blood vessel, or sometimes they go between cells to the actual blood vessel. So here's an idea of passive versus active. These two forms are passive transport. That means these molecules are going to go with their gradient and no chemical energy is going to be used to get the job done. Active means we have to use chemical energy to get the job done. Sometimes it's just that the molecule isn't very permeable across the membrane. Sometimes it's, we're trying to stockpile something, and so we have to kind of force it. In the case of water, water is going to move by osmosis. Okay, water is permeable across the membrane. It has aquaporins that allow it to move across the membrane. And as long as there's a gradient for water, it'll flow. Also, some structures like the collecting duct, their permeability of water can be altered under hormone manipulation. So whenever water travels, it's going to be osmosis. And we're going to look at water moving specifically in the loop of Henle. But remember, most of the way, water can be reabsorbed. Small ions and fat-soluble molecules that are also small are also permeable across the membrane, so they just diffuse across the membrane in accordance with their gradients. When it comes to moving nutrient molecules and a few of the larger cations, we're going to have to resort to active transport pumping. So this is showing you some of the mechanisms. Okay, don't worry about the difference between primary or secondary active transport. To us, it's all active. So you can see we're pumping sodium and glucose. Okay, you can see urea, small fat-soluble molecules, water, ions are just diffusing across the cell and then diffusing across little carriers between cells sometimes. When it comes to the sodium, sodium tends to act as a symporter. The reason why we see sodium reappear so often in reabsorbing is a lot of times we tie chemically the movement of sodium to the movement of something else. So like this purple pump right here, it's pumping sodium with glucose. Or we'll get sodium with amino acids. So that's why you tend to see sodium get moved a lot, because sodium is used to also move something else. Now in lecture I also talked, well, that's pretty much reabsorption, by the way. The job of the simple cuboidal cells in the tubule is to allow diffusion of that which is permeable and have selective active transport pumps in the membrane so that they can grab glucose out of the filtrate and pump it to the blood. Grab an amino acid, pump it to the blood. When you do all of that, that's reabsorption. It's just the selective choosing of molecules in the filtrate to return them to the blood supply. Now for the molecules that are not reabsorbed, they end up hitting the toilet. So whatever you leave behind is not going to be saved, obviously, and it becomes part of the urine. Our ability to move things like glucose is dependent on the number available proteins we have for it. And if you have more those molecules in the filtrate, you hit what's called a transport maximum. You can't pump anymore. So in class I said, imagine I had 100 glucose transporters. That means at any moment in time I can only move 100 glucose molecules. If I have 200 glucoses, I can still only move 100 because I only have 100 proteins. The other 100 are going to hit the toilet. Now, what helps determine things that get reabsorbed versus things that don't get reabsorbed is size. Okay? The larger the molecule is, the harder it is to reabsorb it. Molecules that are not lipid soluble, okay? So things that are not made of lipids, that means you're going to have a carrier protein because lipids can diffuse across water and small ions, but like an amino acid and glucose can't diffuse across. They're not permeable. So we have to have carriers for them. There are other substances that we really just want to get rid of. They're waste. And that's urea, creatinine, and uric acid. We expect to find those in your urine because they're waste materials and we're trying to get rid of them. Okay. There are some molecules, like these three, that are considered indicator molecules. We expect to find them in the urine, and so we can use them as a test of renal clearance. Don't memorize the math formula, but just understand the concept. It's a function of how much, let's just say urea, how much urea is in the urine, the rate of urine formation, the filtration rate, and how much urea was in the plasma to begin with. And they smash all those numbers together, and they get a renal clearance. And renal clearances in an individual can be compared to what's expected or standard. If the renal clearance in the patient is less than the standard, they're doing too much reabsorption. Something's wrong with their ability to regulate filtration, and it's too slow. If their renal clearance is greater than the standard, they're doing too much secretion. Okay, they're throwing things out willy-nilly, or their filtration rate, it's not right either. So either way, if we're too far away from the standard, it's an indication of pathology. And that's all you have to know about clearance. And I should move the slide up one of these days. Remember, the reason why we see sodium show up so much is we use it to run a pump, we use it for facilitated diffusion, we use it as a sim porter, we use it just for tons of things. Alright, so if sodium is so critical because A, sodium helps us move water, right? Where sodium goes, water follows. And B, sodium helps us move things like glucose. So controlling sodium movement is a really critical part of controlling reabsorption and secretion and water balance and things like that. So in addition to things like aldosterone, we have somebody who acts the opposite of aldosterone. We have ANP, atrial natriuretic peptide. In lecture I said, based on its name alone, where do you think this comes from? And everyone figured it out, the heart. Okay, so the heart secretes this. The goal is to lower blood sodium, okay? Whereas aldosterone increases sodium reabsorption, this one inhibits sodium reabsorption. You're trying to get sodium out of the body. Well, if I get sodium out of the body, water's going to go with it. So we use AMP to lower blood volume and lower blood pressure, whereas we use aldosterone to raise blood volume and raise blood pressure. All right, Then we said, let's take the loop of Henle as its own special instance, and then everyone bugged out on me today in lecture. The goal of the loop of Henle is to reabsorb water by osmosis, and everyone's usually pretty cool about that. And remember, we have two parts of the loop of Henle, an ascending limb and a descending limb. And so what you would find is these loops of Henle here. Here's the descending limb, ascending limb. So imagine in this renal pyramid, grab a different color. Imagine in this renal pyramid a whole bunch of loops of Henle. Well, can you notice a difference in the saltiness in the milliosmoles here, the osmolarity? Notice how way out here in the cortex it's relatively low, but as we get toward the papilla of the renal pyramid, it becomes high. Well, the reason is, again, that loop of Henle. On this side of the loop of Henle, we actively pump out salts. Sodium, chloride, potassium. So we're going to pump out a whole bunch of salts here. But we don't move water. That creates a salty environment. And so that's why you're seeing from 300 to 1200 this difference in milliosmoles here. Is because as you get closer to the end of this loop of Henle, you're getting more and more and more salts concentrated. Well, why do we do that? In having this high and increasing salt concentration here, we create a gradient so that on this limb, which is permeable to water, water moves out of the filtrate toward the salt. So the loop of Henle is kind of tricky because on the ascending limb, it's permeable to salts, but water doesn't move at all. So that allows us to make a salt gradient. And you can see how the gradient changes as you move through the medulla. That salt gradient is what's generating osmosis of water on this side. On this side, no salts move, only water can. So the loop of Henle kind of becomes a positive feedback loop. As filtrate comes down on this limb, on the descending limb, water begins to be pulled out. By the time you get down here, you're dealing with a filtrate that's getting less and less water, and so it's kind of saltier. So you start to pull salts out here. Tons of salts come out at first. And as it goes up and up and up, slightly less salt. But we're creating a salt gradient on this side. So by the time the filtrate comes here, it's low in salt. It's also low in water. So again, filtrate enters, water comes out. And so the filtrate becomes salty. And over here, we pull the salt out, which allows you to pull more water out with the next batch of filtrate. So that filtrate becomes salty. So we pour more salt out, which sets up a big gradient so that we can pull more water out and make salty filtrate so that we can pull more salt out. See how it goes? Now, whereas normally some of that salt would diffuse away, the salt here, this environment is maintained because of this specialized capillary, the vasa recta. Okay? Whereas filtrate moves in that direction, blood in the vasa recta moves in the opposite direction. And on the vasa recta on one side, salts can diffuse out of it and in of it. On the other side, water diffuses in and out of it. So the goal and the purpose of the vasa recta is to help us maintain the osmotic gradient. Okay, so that's, if I were to ask you about the vasa recta in lab, I might ask you to identify it. But in lecture, I might ask you about its functionality, and it's about maintaining the osmotic gradient. So one of the things you can do if you want, I said in lecture, I'm not a fan of like diagrams with a bunch of numbers on it, but sit with this, understand how on this side we're moving salts, and how on this side we're moving water. See how this is the descending limb, and as you pull more and more and more water out, it becomes saltier and saltier. So now we come up here, we pull salt out, and we can see the salt concentrations go down as you move back up again. So salts on the ascending limb, but water on the descending limb. So when it comes to secretion, secretion is pretty much the reverse of reabsorption. We don't get to go into it that much because it's fluid and electrolyte balance is a whole other chapter in our textbook. Hold on. Okay, so again, secretion is the opposite of reabsorption. It's just the reverse. We're still relying on active transport. It's still highly regulated. You're still secreting very specific molecules. Essentially, what's getting secreted is waste molecules or trash, things that we might have missed when we filtered the first time. At any moment in time, only about 20% of the blood plasma is actually getting pushed into a nephron. And so that means, a good 80% of it didn't. So it's our second chance to get trash and throw trash away. So we do use secretion to control blood pH, because we use secretion to control getting rid of hydrogen ions or OH ions. We secrete urea and uric acid, excess potassium ions, and again, anything else that's considered waste. And as always, why would we regulate secretion? Well, we regulate secretion because it helps us regulate osmolality, the number of solute particles in a liter of water. How much solute is in our blood. And that's important because that helps determine how fluid moves through our body. So we want to control that highly. Because it, again, related to osmosis. We also want to control, the fluid compartment. And so, the importance of regulating all this stuff is that at the end of the day, your kidney controls the volume of your blood and the osmolality or the concentration of solutes in your blood. And so we need to regulate that because that's tied to diffusion and osmosis and transport and capillary dynamics. That's tied to everything else. That's why individuals who have kidney disease end up having to go on dialysis. Something has to control all these molecules in the blood. So again, we come back to this concept of moving molecules. Let's focus just now on collecting duct. And collecting duct has the ability to either reabsorb water as you need it or secrete it, as in not reabsorb the water when you don't need it. And the real thing that determines this is a hormone called ADH. So ADH acts on the collecting duct. And ADH stimulates sodium reabsorption or water reabsorption. Okay, so we can see molecules moving here. All right, what's the beauty of ADH? When you secrete ADH, you reabsorb water, you make a concentrated urine. When you block ADH, you let water come out. You leave the water in the filtrate, you make a watery urine. So ADH allows you to save water. So you secrete it at night so that you don't have to get up and urinate all night long. You secrete it in times of stress in addition to aldosterone. You secrete it if you were dehydrated. And if you've ever had the experience of making a dilute urine, that comes about because water and sodium go out through the filtrate, and that's a lack of ADH. And the collecting ducts just aren't permeable to water or sodium, so it stays in the filtrate. If you want a concentrated urine, you're going to make ADH, reabsorb water, make the collecting ducts permeable to water. And then I said, for fun, let's look at some other diuretics. We talked about glucose and the fact that where glucose goes, water follows. So when someone has glucose in the urine, that means water's going out in the urine as well. We talked about alcohol and the fact that it's a vasodilator, so you're going to increase net filtration pressure. You also block ADH. Caffeine, very similar, vasodilator, blocks ADH. Most diuretic drugs also will block ADH or vasodilate, and some of them inhibit sodium symporter, so you can't reabsorb sodium. And I keep forgetting to delete this one. We talked about renal clearance already and the fact that we can use it as a gauge of reabsorption and excretion. And now that we've made all this urine, we have full bladders. So now we look at how we evacuate the bladder. The reflex that controls that's called your micturition reflex. So imagine your bladder filling with urine. When it reaches a certain stretch size, like you stretch the trachome, you stimulate the reflex. So you don't have to memorize all the pathway, but it is a reflex, and I'm going to go on the assumption you remember what reflexes are from your previous AMP1 life. But this is the micturition reflex. Its stimulus is a full bladder, a bladder that's been stretched. And the response is you open your internal urethral orifice. I did it again. Internal urethral sphincter, and then you contract the detrusor muscle. We have an external urethral sphincter as well. It's voluntary control, so you can wait to do this until it's convenient. If you need to store the urine, then you don't fire the reflex. Or if you ignore it, we talked about the fact that it comes, you can ignore it, it goes away for 20 minutes. So we can kind of inhibit this reflex for periods of time to increase storage. There does reach a point where you just can't add any more urine to that bladder. And if that was in the middle of the night, that's the point at which you have the dream that you're going to the bathroom. Or you're in such discomfort that you just can't take it anymore. Right, so that's the end of the urinary system. Hopefully that helps you be able to practice the factors and the regulation of filtration and the factors for reabsorption. Filtration is basically, kind of a simple concept. I'm not going to show, but it's kind of a simple concept in that filtration is going to be dependent on pressure gradients. Manipulate the pressure gradient, you manipulate filtration. Reabsorption comes down to recapturing useful molecules, and they can either diffuse or be pumped. The loop of Henle comes down to the fact that one side creates a salt gradient, the other side allows water to move. The collecting duct can reabsorb water and salts when ADH tells it to. So that's kind of the basic pathway.